Hello again. This is Math 1120 coming to you from the College of DuPage. The title of this lecture is Relative Velocity Along a Straight Line. As always, please be an active learner as you watch this video. Relative velocity along a straight line. We always describe the position and velocity of an object with reference to a particular coordinate system. When we speak of the velocity of a moving car, we usually mean its velocity with respect to an observer who is stationary on the earth. But when two observers measure the velocity of a moving object, they get different results if one observer is moving relative to the other. The velocity seen by the particular observer is called the velocity relative to that observer, or simply the relative velocity. This picture down here where you see a cyclist who is stationary, a train that is moving past the cyclist, and a woman on the train that is walking shows an example of the concept of relative velocity in action. In this example, we'll assume that all the motions are along the same straight line, the x-axis. A woman walks in a straight line with a velocity, x component, of 1 meter per second along the aisle of a train, but the train is moving along the same line with a velocity of 3 meters per second. What is the woman's velocity? This seems like a simple enough question, but in reality it has no single answer. As seen by a passenger sitting on the train, she is moving at 1 meter per second. A person on a bicycle standing beside the train sees the woman moving at 1 meter per second plus 3 meters per second, or 4 meters per second. An observer in another train going in the opposite direction would get still another answer. So you see, the velocity is different for different observers. We have to specify which observer we mean when we speak of the velocity relative to a particular observer. The woman's velocity relative to the train is 1.0 meters per second. Her velocity relative to the cyclist is 4.0 meters per second, and so on. Each observer, equipped in principle with a meter stick and a stopwatch, forms what we call a frame of reference. Thus, a frame of reference is a coordinate system plus a timer. Let's look at a slightly more complicated example. So here, E stands for the expressway, and U are in a car, and we're only going to have two frames of reference here. So you are driving along a straight two-lane road at a constant speed of 88 kilometers per hour, and that is your speed U, Y, relative to the expressway. So you're moving 88 meters per second. But a truck traveling at a constant 104 kilometers per hour approaches you in the other lane, and it's jokingly say fortunately, because that way it doesn't run into you. So you see the velocity of the truck is going the other direction, and that is the velocity of the truck is v sub t relative to the expressway. That's how fast they're going relative to the expressway is 104 kilometers per hour. So there are two questions we ask. What is the truck's velocity relative to you? And what is your velocity relative to the truck? Okay, well, what happens is the velocity of the truck is approaching you, so it must be going south. So the velocity of the truck relative to the expressway is 104 kilometers per hour, and it is negative because you're taking your direction to be positive. We want to find v sub t of y. And so what happens is that it's going to be the truck's velocity relative to you is going to be the sum of these velocities. So your velocity relative to the expressway is 88, he's going at 104, and together it is 192 kilometers per hour. That means the truck is moving at a rate of 192 kilometers per hour south relative to you. Now, if you do the other kind of thing, you are moving 192 kilometers per hour, but that is north relative to the truck. So you see, relative motion is important consideration. As we will see later, now actually you might see this in later physics courses, we will talk about this theory of relativity. But relative velocity relationships do not hold for objects that are moving at extremely high velocities because you cannot go faster than the speed of light. In particular, when velocities are near the speed of light, we no longer can simply add and subtract them. This is what Einstein studied in his theory of relativity. This is because nothing in nature can travel faster than the speed of light. And this surprising and somewhat counterintuitive fact was first predicted by Albert Einstein's special theory of relativity. And the book will talk about that later, although that's not what we will cover in this ultrasound course. Let's test your understanding of these concepts with a question. And this is a multiple choice question, although I don't usually give multiple choice questions. This is about a truck caravan. 3 trucks are traveling eastbound in a positive direction in the same lane. The speed of the front truck is 80 miles per hour, the middle truck is 70 miles per hour, and the rear truck is 67 miles per hour. What are the relative velocities of the front and rear trucks as seen by the middle truck's driver? And you have 3 answers that you can, 4 answers, excuse me, A, B, C, and D that you can choose from. You know what to do. Let's see how you did. Well, from the middle truck driver's perspective, the rear truck is falling behind at a rate of 10 miles per hour. So its relative velocity is minus 10 miles per hour. Similarly, the front truck is pulling ahead at a relative velocity of plus 10 miles per hour. Therefore, the correct answer is C to the question. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.